Welcome. This is the first part of a series on an introduction to the derivative. In this series, I'm going to use examples and problems largely taken from the text Larson Edwards Calculus of a Single Variable 9th edition. But the concepts presented here will be universal, so regardless of the text you have, you'll be able to follow along. Now, the first part of this is we're going to talk about one of the fundamental problems in all of calculus, and that is the tangent line problem. So let's say that we have a function, some function f, and we take some point x, and the value of x on that function is, of course, f of x. F evaluated at the point x. Say we have a second point offset from the first one by some distance delta x, and that point's value on the function is f of x plus delta x. Now if we connect those 2 points on the function with a line, that line is called a secant line, and the secant line gives us a very rough approximation to the slope of a tangent line to the function at point f. Now I say very rough approximation because that is the nature of the tangent line problem, that this approximation gets better and better as this point approaches this x value. So let's give a little bit more dramatic example of that. Here we have our secant line, our x and our x plus delta x values, our f of x and f of x plus delta x. Now, when I drag this point closer and closer to the x value, you can see that the delta x value is diminishing. The slope of this secant line is becoming a closer and closer approximation to the slope of a tangent line until the delta x value is actually 0. And when the delta x value is 0, the slope of the secant line is equal to the slope of the tangent line. And that's at the root of what we're looking at here today. So let's go back and see if we can figure out what all this stuff means. We're talking about the slope of this secant line. So the slope of the secant line is given by the change in y over the change in x. In the context of our diagram here, the change in y is going to be this value minus this value. So this distance minus this distance gives us this change in the y value. So what we have is f of x plus delta x minus f of x over the change in the x values. Well, the change in the x values is just x plus delta x minus x. So x plus delta x minus x. And if we simplify this, what we come up with is f of x plus delta x minus f of x all over x minus x is 0, and we're just left with the delta x term. So this is known as a difference quotient, and what it is basically the slope of the secant line. Okay. Now, if we want to determine the slope of the tangent line, we've got to bring this delta x value down to 0. Now, through your investigations of limits, that is the very heart of the limit process. So, in fact, what we're looking for, if we want to find the slope of the tangent line, we've got to take the limit of this expression as delta x approaches 0. So, the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. And this is actually the limit definition of a derivative. So in essence, the derivative of a function gives us the slope of the tangent line at any point on that curve. Now, there are many ways to denote the derivative. One of the most common is f prime of x. It's given as the first derivative with respect to x. So that's going to equal the limit as delta x approaches 0 of the difference quotient f of x plus delta x minus f of x over delta x. Other ways to denote this beyond f prime of x is the derivative of y with respect to x, or y prime, or the derivative with respect to x of some function f of x. These are the most common ways that you'll see the first derivative denoted. And we're going to be using all of these throughout these discussions. So we'll get kind of used to seeing the different forms. So let's take a look at a specific example and see if we can put this into more concrete perspective. So in this example, we want to find the slope of this line. Well, because this is a linear function, the slope of this line is in fact, the line is in fact the tangent line to the function. They're one and the same. So employing our limit that we just looked at, we could find the slope of this. So take the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. Now, as you can see, this is a composition. So wherever we're going to evaluate the function f, which is given by this expression, at the value x plus delta x. What that means is we're going to take this x value and replace it with x plus delta x. So that's the general process we're going to use when we employ this limit definition to finding the slope of a tangent line or in finding the derivative. So to make this substitution, the limit as delta x approaches 0. Now here we're going to take the x plus delta x and put it in for x. 2 times x plus delta x. You can see the substitution here. Minus 3 minus f of x. Now I like to use parentheses a lot just to avoid making simple sign errors. All over delta x. Now let's go ahead and simplify this through, and we have distribute the 2, so 2x plus 2 delta. That didn't work out so good. 2 delta x minus 3 minus 2x plus 3 all over delta x. Now, if we did our work properly, what should happen in this difference quotient is everything should cancel out except terms that have a delta x in them. So here we have this 2x and this 2x cancel out. This negative 3 and this 3 cancel out. Then we have these terms with the delta x. So we have 2 delta x over delta x. And of course, these guys cancel out. And so our final result is 2. Now, of course, we take our limit all the way down here, and the limit as delta x approaches 0 of this is simply the same thing, because there is no delta x term here. So the slope of this expression is 2. And I'm sure you already knew that from the beginning, but this shows an example of how we can analytically find it using our difference quotient and the definition of a derivative. So let's move on to another example. In this example, we want to find the slope of the tangent line of this function at the points 0, 1 and negative 1, 2. To find the slope of the tangent line, we're going to use the limit definition of a derivative. So the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. We go ahead and substitute this in here, and we have x plus delta x squared plus 1 minus x squared plus 1 all over delta x. Now we need a binomial expansion for this, which is x squared plus 2x delta x plus delta x squared plus 1 minus x squared minus 1 all over delta x. Now let's do some simplification here. We can see that this x squared and this x squared go away. 1 and negative 1 go away. We're left with 2x delta x plus delta x squared all over delta x. Here we take away our delta x terms, so this cancels that, and we have 1 here. So we're left with 2x plus delta x. Now we carry down our limit and take our limit here. As delta x goes to 0, this term goes to 0, and we're left with 2x. Now it's very important to see that the derivative of this function generated another function. This function will give us the slope of the tangent line of this function at any point. So that's all we have to do, is substitute this coordinate into this function. So 2 times 0 equals 0. The slope of the tangent line of this function at 0, 1 is 0, and 2 times negative 1 is negative 2. So the slope of the tangent line of this function at this point is going to be negative 2. So that's a brief introduction, and we will continue with our introduction to the derivative in the next session.